Hi, welcome back. So we've got a fairly long problem in front of us. I'm not going to spend a lot of time with introductory comments because I want to get into it and work our way through it. It's kind of a comprehensive question because it's going to take us through most of the calculations that we might include in a classic flexure problem. In this case, we're looking at shear flow or trying to determine or using shear flow in this case to determine the number of nails we need in our beam to hold it together. And so we have a laminated or fabricated inverted T using a series of nails lined up along the center line as shown in the cross section. We have a shear capacity for each of the nails at 1.4 kilonewtons per nail. And so now what we'd like to do is to walk through the essential steps to resolving the question, what's the required number of nails, or what's the spacing for these nails? And we can figure that out. So let's jump right into it. It's a similar configuration to some of the other examples we've used, but the values are slightly different. So we're going to start it from first principles and go right through it, start to finish. So the first step, inevitably, free body diagram, use our static equations to solve for reactions. So let's get the free body diagram drawn in. So pin end at A. Oh, so we don't have labels. So let's label these A, and we're going to call the point of load application B, and C over at the far end. And now we're ready for our free body diagram. So we have two possible reactions or components. At A, we have reaction AY, reaction AX. We have a single possible reaction at C, which is in the vertical. So reaction CY. And then we have our externally applied force of 3 kilonewtons there. And that, for the most part, is our free body diagram. And so we're happy with that. I think I'm just going to add to it our x-axis in case we need it. We can draw in a y-axis, if you will, here, just to show where our x is equal to 0. And let's get right on for solving for reaction. So we can do the trite one first. So we can say sum of the forces in the x direction is equal to 0. And that tells us that RAX is equal to 0. That's kind of obvious, and we could have just probably written that in there. It depends on the level of rigidity you insist upon. And then let's go ahead and solve for our reaction at y by applying our sum of the moments about A equals 0. We'll use our clockwise positive. We'll set it up. So about A then, RAX, RAY don't count because their perpendicular distance is 0. So we have our 3 kilonewtons externally applied force with a moment arm of 1 meter. And RCY is trying to go counterclockwise, so we'll put it in as negative, and it has the full length moment arm of 3 meters. And we're able to resolve RCY is equal to 1 kilonewton. And we can get our last reaction just by using our last equation. Sum of the forces in the y direction is equal to 0. So we have RAY minus 3 kilonewtons plus RCY, which we know is 1 kilonewton. So RAY is equal to 2 kilonewtons. Just identify these. And I'm going to go over, put them in my free body diagram. And we're good there. The next step, I'm going to use the graphical method to get to the shear force and bending moment diagrams. So I'm going to do it fairly quickly. We've done it several times in the past. So we're starting at A, going up to 2 kilonewtons. And then it's constant across until our point load is applied. It pushes it down 3, takes us to -1. And then that takes us across to our final point load, which takes us back up to 0. Let's label some values in here. We have 2 and we have -1. And you can go get the areas, if you will. Area is equal to 2 in there. Area is equal to -2. And so we're going to do our bending moment diagram. So change in moment between A and B is equal to the area of the shear force diagram, which is 2. So this is going to take us linearly up to a value of 2. And then we have -2 between B and C. So that takes us back down to 0. And so we have both our shear force and our bending moment diagrams, which can tell us what the maximum shear force or maximum bending moment is and where it occurs in the beam. And that's where we're going to design our cross section so that we get it for the worst case conditions. So we've got that. We need a couple cross-sectional properties to make this all work. So let me just go section properties. And so the first thing we need to do is to figure out what the centroid is. So I'm just going to quickly put a slightly larger sketch area together for our cross section so we can draw on it and see what we're doing. So just give me a second, I'll get that done and then we'll carry on. Okay, so I've drawn out our cross-section slightly larger than it is, and that way I can mark on it. I've also gone ahead and put the dimensions on it so we can see that. And I've marked in the first of the section properties, which we're going to want to calculate, which is our distance from the bottom to the neutral axis, or indicated here as y bar. Now we have two obvious geometric shapes making up our cross section, two rectangles, so general rectangles, which are great. They make them easy to work with. And so I'm going to identify them, and I'm going to do them as area 1 being the web, if you will, and area 2 being the flange area. And I'm just going to hatch them out so you can see the full up area that I'm describing. There's area 1 and area 2. And with that, I think we're ready to get underway and to figure out what the actual value is for y bar. And so I'll just write out the formula to start with. So we have y bar, and we know that y bar is equal to the sum of a at I, d at I, all over the sum of a and I. So each of these represents an individual section. So we have two sections, the web and the flange. And so we have to know what D is. So D is going to be the distance to the centroid of the individual section. So rectangles are easy. It's halfway up the height or halfway in the width for the centroid. So let's mark where the centroid would be on number 1. So right through there, and the centroid through number 2 right in here. And so this distance in here would be D2, and that's equal to 10 millimeters, or half the height of the flange. Let's extend this line out just a little bit further. And this distance in here is going to be D1, and that would be equal to half the height of the web, which would be 70 millimeters, but we have to add the 20 millimeters of the flange to get to the start of the web. So that would be equal to 90 millimeters. And with that little bit of analysis, I think we have everything that we need to do to solve this. So we're just going to run across here. We'll start with number 1. So the area of 1 is 140 millimeters multiplied by its width, which is 20 millimeters, multiplied by D1, which is 90 millimeters. And then we do the same thing for our flange, or area 2. We have 100 millimeters wide, 20 millimeters thick, and a D2 of 10 millimeters. Let's get a little bit long here, underline that. And then just the area under that, so we can just drop the D's off, 140 millimeters times 20 millimeters plus 100 millimeters times 20 millimeters. And we can figure out what our Y bar value is, and I get a value of 56.7 millimeters. Yeah, I can write that in here. Now, the other property we need to know is our moment of inertia, or the second moment of area. And so we're going to work with the same areas, 1 and 2, but the distances that we're interested in are not from the reference plane at the bottom, but rather from the neutral axis. And so what I need to know is the distance between Y bar and that centroid in 1. So really, I'm going to change to a different color here. Where am I going to go? And that distance is in here, and that, fortunately, is also a D1, and that's equal to the 90 minus 56.7, and I get a 33.3 millimeters. And then to area 2, we have this distance down here, D2, and so that's the 56.7 minus the 10, or 46.7. And with those values, I think we're in a good space to get this. So let's just label what we're doing. So we're looking for moment of inertia, or second moment of area. And so we're going to be using the parallel axis theorem for this. So we know that I total is equal to I not, so over its that area's moment of inertia about its own centroidal axis plus its area multiplied by the distance between the composite sections, centroidal axis, and centroidal axis of the specific area we're talking to. And that D value is, of course, squared, which gives the big impact to the parallel axis theorem. So with that said, we can go ahead and do this for our section. So we need to know area 1. And of course, area 1, I'm just going to recall for a rectangle, I'll call it not in this case, is equal to BH cubed over 12, which we derived somewhere along the way. So that's going to cover off that first term, and then we have to deal with the AD squared terms. So for our web, our width is 20 millimeters, and our height is 140 millimeters. So that gets the benefit of the cubed divided by 12. And we'll add its area, which is 20 millimeters, 140 millimeters, all times d at I squared. And so we said for, in this case, D1 is 33.3 millimeters, and that is squared. And to that, we have to add our second term. I'm just going to drop down here. So plus our BH cubed over 12 for the flange, or area 2. So in this case, our B is the width is 100 millimeters. Our H is 20 millimeters, and it is cubed divided by 12. And we'll add to that the area, 100 millimeters times 20 millimeters, all times D2, which we wrote down as 46.7 millimeters, and that gets the squared term. And so that's the full application of the parallel axis theorem and provides us a value for I of 12 times 10 to the 6 millimeters to the fourth. I'll go up here and get that too. They're all intermediary solutions. One other section property that we have to concern ourselves with, and that's the first moment of area, or Q. And of course, that varies over the cross section, so we have to do Q at a particular point. Now, the Q where we're interested in this case is at the interface of the flange and the web, because that's where the nails are going to be carrying the shear, or the shear flow. And so what we need to do is to calculate Q for that interface. So let's just over here, first moment of area. And so I just do one at web flange interface, just so that we remind ourselves that this is varies over the cross section and we're doing it for a particular point. Okay, so when we calculate our first moment of area, and I've done a video specifically on that cross-sectional property. It's a fairly popular video, so if you're still struggling with Q and how to get Q and everything else, by all means, I will go over it here, but I will put up a card up here for you to go back to that video in case you're still need a little bit of clearer understanding, where I go through it really slow time deliberately for the purpose of understanding its calculation. In this case, I'm going to go through it fairly quickly. So of course we basically ignore or throw away one side or the other of, from our interface that we're drawing. And so we're drawing the interface in this case at the flange web interface. And so I'm going to choose in this case to throw away everything above that. So all of what we've previously referred to as area 1 is gone. So I'm going to look at area 2 alone. I'm going to still call it area 2 just so we don't get confused. So we're only looking at the area in here. We still need its distance from the neutral axis to its centroid, which would be this distance in here. And we've already said that that's equal to 46.7 millimeters. And that's about all we really need to get through this specific calculation. And so so our value Q is equal to the sum of A at I, D at I for the first moment of area. And so we only have one side or the other of that interface line, so we're going below it in this case. And so our area is the area of area 2, which is that 100 millimeters times its thickness or depth of 20 millimeters. And its D at I is 46.7 millimeters. And we get a value of 93.4 times 10 to the third, and units for that are millimeters to the third. So with that, we've actually got ourselves down to the point where we can go ahead and calculate shear flow. So calculate shear flow. And again, we're calculating it at that flange web interface. So our shear flow, which we've denoted by the small letter q, is equal to V times our first moment of area divided by our second moment of area, or moment of inertia. So we are going to do this for the point of maximum shear. So we go up to our shear force diagram. We see that the maximum shear occurs between A and B and is equal to 2 kilonewtons. So we use that in here, so 2 kilonewtons between A and B. And then we take our value of Q, which is 93.4 times 10 to the third millimeters to the cubed. and we divide it through by I, which is 12 times 10 to the 6 millimeters to the 4th, and we get a shear flow of 0.0156 kilonewtons per millimeter. And really what that is telling us, for every millimeter of length along the beam, we have to resist a shear force of 0.0156 kilonewtons. So the easiest thing to do is to calculate what spacing we would require for our nails. So our spacing then is equal to the capacity of each nail, so V of each nail, divided by our shear flow, or the capacity required per millimeter. And so we get our 1.4 kilonewtons, which was given in the problem, as the capacity of each nail, divided by 0.0156 kilonewtons per millimeter. And we realize that we can get a spacing of 89.74 millimeters between nails and still have the nails do okay. Now, that's very close to 90 millimeters. I would probably round that to 90 millimeters. However, we always want to round to conservative, so I'm not going to round it up. I'm going to say, no, round it down. We want their nails closer together than farther apart, so that we don't actually exceed them. And so in this case, I'm going to say use 85 millimeters spacing. Now, the actual question asked us what the total number of nails are. So we have a beam which is 3,000 millimeters long. So number of nails is equal to our length divided by our spacing, which is equal to 3,000 millimeters divided by 85 millimeters, and that's equal to 35.3 nails, and I will round that up to 36 nails. So there you have it. We've been able to figure out or use shear flow to figure out the spacing of the nails. Now, what you probably noticed is that the actual shear flow, let me see if I can get the whole problem on the screen. The actual shear flow component of the question is one or two short formulas at the very end, and we're able to figure out what the spacing is for the nails and that. The rest of it is really all of the fundamentals of flexure that set you up to that final calculation. You have to do your free body diagram. You have to get your external reactions. You need to do your shear flow diagram. You need, your shear force diagram. You have to do your bending moment diagram. You need to have the cross-sectional properties if they're not given in the problem. So you're going to have to calculate your Y bar. You're going to have to get your moment of inertia or first moment of area I. You're going to have to get your second moment of area Q at the interface where you're interested. So all of that goes into the problem. And in this way, you'll see how in mechanics of materials, everything builds on everything from before. So you can't have a weakness early on and then still be able to expect to progress. You're going to have to master those early skills, those early bits of knowledge, so that you can get to the part of the problem which is actually being asked. So that's it for this question. I think other than some of the review problems coming up, we're done with flexural stresses, because we've looked at normal stresses, we've looked at shear stresses, we've now looked at shear flow, and we're going to move on from here and start looking at combined loads, where you're going to get axial forces combined with shear forces and flexural forces and that type of thing. And so with that, I'll leave you off. I'll give you a link to carry on with the next problem as it comes up, and we hope to see you there.